This is EE370, lecture 14. So I could see that there were a lot of confusions regarding the finite state machine and data path in the tutorial session. So I thought I could quickly tie up certain points. So let's still consider the same question for which we solved in the previous class, right? We constructed a data path for it in this manner, and we designed a control path in this fashion. Right? I think individually the construction of data path and control path, are there any questions? I hope it is clear. Right? So now how you would put all of this together is, let's say this is your whole system. You will have your data path here, which is the data path that we designed, and then your control path will be implemented using the FSM. Inputs like clock and reset are common to both the data path and the control path. The input A in and B in will go into the data path registers. The input start signal, which tells our FSMD you can start computing now, that has to be fed into the control path. So this goes into the control path. Now the final output of the system, which we said would be a ready signal and an out. The out signal will have, the out register will have the final output after the computation. That is going to come from the data path. In this particular problem, the value of A, the value stored in the register A at the end of the computation cycle, that was your final output. Right? So that goes from your data path to the output of the system. Whereas the ready signal, which tells you that the computation has been completed, has to be generated within this FSM. So that comes out of your FSM module. Okay. And once you have a state diagram like this, you now know how to translate it into a combinational circuit plus flip-flop configuration. Right? You would do state minimization if necessary. This looks like the minimum number of states you can do this operation with. But you can still try state minimization, and you can see if it is possible to further reduce down the states. So state minimization, then you will do state assignment, then you will construct the state transition table, which shows how the next state is to be, the inputs to the flip-flops, such that the next state is computed correctly. And then finally, you will also have some combinational logic for the output. And if this is a Moore machine, which is what we had done the state diagram for, then you have this memory element which we implemented using the flip-flops. That will have the output as the present state. Right? That is your state variable when we wrote our Verilog. Right? So this will have what state you are in. Are you in S reset, S start, S compare, S loop, or S ready? Right? Given that we have 5 states, how many flip-flops do we need to store the state information? Can I do it in one flip-flop? How many flip-flops do I require? We need 3, right? 5 states. So if you use only 2 flip-flops, that is 2 bits, which means you can have only 4 states. Therefore, you need to have 3 flip-flops. With 3 flip-flops, you can have up to 8 states, but 5 states are sufficient for us. So which would mean that here when I say present state, it's actually not 1 bit, it is a 3-bit information. Now, to set up the next state variable, you would use your inputs and the present state value, and you will have some combinational circuit that feeds into the D of the flip-flop. For your outputs, because this is a Moore machine, from the present state variable, you will have some combinational circuit, and then you get your outputs. Right? So in effect, in this diagram, now you will have a combinational circuit plus memory element. So in effect, a sequential circuit as your control path. The inputs to this circuit will include A greater than or equal to B, the signal that is coming from the data path. And you will also need the start signal. The start signal should also become an input here. Right? And finally, the outputs of the system are the ready, load A, load B, update A, of which ready is going as the output of your whole FSMD, whereas load A, load B, and update A are going as inputs to the data path. Right? Is this any questions on this? I'll give you 30 seconds to stare at it and ask me any questions. Yes.
It will also be correct if I just keep on giving A as an input to the control path and out from the control path output also.
But why would you?
Things, but it will be correct.
Your system will work.
Yeah.
Right? That is true. So this distinction of calling certain portions as data path, certain portions and control path, it's up to the designer to do it. Right? It's not like there is one correct solution or one incorrect solution. There are a lot of correct solutions. As long as the system works, it is one of the correct solutions. Right? But like you mentioned, taking out from here, right? This register has your final result. Now you take it from here, you feed it to the control path. Maybe you are storing it in another register or routing it like this, right? It is slightly looks more complicated than the simpler diagram, but that is not an incorrect solution.
I mean, in the quiz, I would count as an input to the control path and to output as like out from the control path. I wrote the same justification that
should be okay. So when we evaluate the full answer, then only I can comment on.
I mean, it's right that we can directly forward count.
Then it is. If you have explicitly mentioned it, then it is.
Not an input of output of the control.
If you have written it explicitly, then it is. And similarly, it is not necessary that you have to make sure your controller is purely Moore or purely mealy, right? You could have, for example, if I do like this, then all the outputs are a function of only the present state. Maybe I decide that I want some of the outputs to be a function of the input as well as the present state. I could do this. Right? So some outputs can come like this, some outputs could come out of the combinational logic like this. So this is then a function of input as well as the present state. Then your controller has a combination of Moore and Mealy. That is also fine if your system is working. You should have that skill of being able to switch between Moore and Mealy so that when the time comes you can do it effortlessly. That's all. Instead of computing A greater than or equal to B, you are using the leftmost bit, is it? So what is your logic?
Because when we take the difference from PIP, it's over 0, but the answer is 0 is still 0, and the A is like greater than B, then also a first.
That is a reasonable thing, right? So all that he is saying is, if you are representing all your numbers in the registers as a 2's complement form, if the number is negative, the MSB is going to be 1, right? Otherwise it is going to be 0. So if A is greater than or equal to B, your MSB bit is always 0. So instead of doing this computation and then looking for it, you directly take out the MSB bit from the output. Reasonable, a very good suggestion. Okay. Any other questions on this? So what you are seeing here now, this is basically a finite state machine and data path is a computing machine, right? It's a computing hardware. Now any problem statement that you take, right, you will be able to implement it in some or the other form of a FSMD. And if you understand FSMD thoroughly, the idea that the registers are being loaded with certain value, and then you sequence how the operations on those registers are happening based on control signals from a controller. So if you understand this concept, now you are only a few steps away from understanding how a microprocessor or a microcontroller works. It's just a little bit of extension from here and you get to a microprocessor and a microcontroller. Okay. So now let's say I want to implement the Moore machine. So the same Moore machine that I have shown here. Let's say I want to implement this in Verilog. Right? How would I do that? So can you quickly tell me, just for this Moore state machine, How many always block will you use? Okay, so let's look at the state variable, the present state variable, right? Can you tell me whether you will declare this as a register or a wire? Is the question clear? So yes, you would declare this as a register because it's a memory element. In fact, this is a D flip-flop which has to be sensitive to the positive edges of the clock and positive edges of the reset, right? The way I have shown the signals here, right? So clearly this is going to be a register. So we will first look at the controller design, specifically the state register, right? So we have always block which is sensitive to positive edges of the clock and positive edges of the reset. Because you have two items in the sensitivity list, your main if else block should correspond to these two conditions, right? So if you are in reset, then you have state value to be something else. This is what should happen in the clock condition, right? So if you are in reset, you are looking at this pin now, your output goes to 0, right? Or a particular value of state that you want it to take. Else you are looking at the clock condition, then the effect of this combinational circuit should appear here, right? Now you can implement this circuit, right, as either a single always block, or you can do this as two separate blocks, right? I could call this variable, let's say I can call this variable as next state, right? And next state is simply a combinational logic output depending on the present state and an input, right? So I can implement this as a combinational circuit where next state is declared as a variable. Would I declare next state as a wire or a register? Wire, because it is a combinational circuit, right? But you can also implement combinational circuit even if you declare next state as a register, right? So now it depends on how complicated this combinational circuit is, right? If you would benefit from using a lot of if else if conditions, or if you will benefit in using a case statement, then it makes more sense to declare next state as a register and then do always at star and then define the behavior of the next state variable. But if the next state variable is, a very easy combinational logic, then you declare it as a wire and then do assign next state equal to something, right? And then in the flip-flop definition, you would assign the next state variable to the state variable, right? But here in this particular code I'm showing you, I have combined the effect of both of these together and I've written a single always block.
If we define the always block only for function, what would be its sensitive to? I mean, if you always start.
Always star means you are sensitive to any signal which is being read inside the always block, right? For example, so if I look at this always block, let's say from here to here, right? This is not sensitive to the edges, it is sensitive to any change in at all, right? The star means at all. Now what does that all mean in this context? It means that if your state variable changes, or if your if your state variable changes, that's it, right? Load A, load B, they are coming on the LHS, they are being assigned to, right? So any variable that is being read in, so if I had another variable on this RHS side or the state variable, when any of these changes, this block is executed. And this has a purely combinational implementation, even though I have declared state variable as a register. So in Verilog, just because you declared a variable as a register, it doesn't mean it gets translated into memory, right? A register can be implemented as a sequential circuit or a combinational circuit depending on how you write your always block. Okay, so let me quickly take you back to the state register. Now you can see that there is a case statement here, right? So the value of the state variable depends on a case statement. And this entire case statement is going to be some sort of a combinational circuit. Okay? So Now, and your state variable has a particular value depending on the state you are in, the current state you are in, as well as some of the inputs that you receive. Clear? Now, can you comment on how your output variables should be? Would I declare it as a register or a wire? Can be register, can be wire. It's combinational circuit, right? So here again I have declared them as registers. So we had load A, load B. I think I'm missing an update. Update A and ready. 4 outputs we had to create. So I used a always H star statement and then always block and then have assigned values to it depending on the different states. I could have combined all of these into a single always block. It is fine as long as I make sure the value of each variable is completely known under all possible conditions. Right? Because your ready, I needed to assign 1 to it only when S ready was the state. I chose to have it as a separate always block. Similarly, the update A, it needed to have 1 only when your state is S loop. I made it a separate always block. But even if you put all of these into a single always block, and you are able to simulate, synthesize, and then do a post-synthesis simulation and verify, that is also perfectly functioning code. Okay. So, any questions on this? Right. Now, let's say instead of putting always at star for all of them, I did always at pause edge of clock. What does this mean circuit-wise? You understood the question? Earlier it was always at start. Now for ready update a signal, I have made it always at pause edge of clock. Right? What does it mean? How did our hardware change now?
Even if any input block now instead of state.
Correct. So what does that mean?
Even if input or something changes, it will not act immediately.
It will not act immediately. It will change at the positive edge of the clock. Right? So can you tell me how I should change my schematic? Is it right to call this as my update now? No, right? Because if I show this as a circuit, it means update A is free to change anytime the present state changes. But that is not our circuit now. We have always set pause edge of clock, right? Which means now I have a flop that is operating at the positive edges of the clock. This signal is being fed as the D input, and the output of this is my update A now. Is that clear? Now your update A can change only at the positive edges of the clock, and it depends on whatever this combinational circuit is implemented. Okay. So what I mentioned at the end of the last class was that when I earlier showed you code of the output, I had put positive edges of the clock even in the code for the output. Right? That was not necessary. In doing that, I introduced an additional flop here. But in a Mealy or a Moore machine, the outputs are coming as the output of a combinational circuit. So always H star is sufficient. Okay, any questions on this? So now let me ask you a slightly different question. Would you consider clock and reset as inputs to this FSM? Right? If I sketch like this, it is reasonable to not assume clock or reset as input to the system. Right? Now, if I had a synchronous system, right, wherein synchronous reset, meaning the reset is not given here, I give the reset also as input to the D side. Right? This is your D input to the flop, which means the effect of the reset is seen at the output of the flop only at the clock edges. So far, we have been assuming that the reset is asynchronous. Anytime reset goes high, irrespective of whether there is a clock edge or not, your output goes low. Right? But if I connect it here, now this is a synchronous reset. Even if your reset goes high, only at the next clock edge will you see the effect. Right? So the reason why I bring it up is because in the first surprise quiz, there was a question whether the state machine was Mealy or Moore. Right? So I had intended it to be a Moore state machine, but one of the inputs was reset. So some of you argued that reset should be considered as an input, and therefore the outputs are a function of reset, and therefore technically it has to be a melee machine. Right? So I agree the question is a little bit ambiguous. Now whether you want to consider reset as an input or not is not very clear. It's something that we need to define. Right? Because finally reset is an input to the system, overall system. Right? It's a different matter that when I sketch the diagram like this, your reset goes here and is not a typical input like the other inputs coming into the system. So because of this, I've decided that I will consider both answers as correct for the final that question. If you had given the reset directly here, then it is an input, right? But since the if we were to give the reset here, right, then it is tricky whether you want to treat it as an input or not. So next time onwards, when you write melee or more, especially if it's a detailed explanation, you can comment on whether you treated reset as an input or not. But for now, both answers I'll give marks. Okay, so one more point I wanted to add was, now here there were questions on whether you should have the compare state or not, right? And there were some suggestions as to how you can bypass this compare state. So if you really want to verify whether it works or not, the correct way to go about it is to implement the circuit and check. Right? But of course, to implement the hardware is going to take a lot of time, lot of resources. So the next best way is to simulate for the behavior, which is where you will implement the circuit that you are trying to construct in Verilog and then simulate for it. Right? So I want you to try and implement this in Verilog. So let's say you remove the compare state. Are you still able to get your hardware to work? Right? To make it easy, I will share the code that I showed now, and then you edit it, remove the compare state, and figure out how you can do it without this. Right? So that is something that you have to try this and learn it on your own. Okay. So then we'll come back to the analysis of, we'll come back to the timing analysis. So far, we had simplified, yes, you have a question? What delays are we talking about? Correct. So if you have this compare state, this is taken care of. In melee, you don't need this, right? You could have created the circuit without the compare state. But in Moore, one of the reasons why I put in the state is so that you have one state delay before, so one clock cycle delay before you start comparing and looking at the result again. So you look at the result, the load outputs will be ready in the next state. So this is why I want you to try out, see if you are able to achieve the correct result, assuming a Moore machine without this compare state.